All right, let's talk about overfitting. Um, how to tell when you have overfitting, why it happens, and then how to prevent it. Things like regularization, dropout, stuff like that. We're going to cover quickly and efficiently. Um, Not trying to teach things from first principles, just a refresher. Okay. So overfitting, what is it? Let me pull in a helper here. Okay. So here we have a binary classification problem with maybe the ideal decision boundary drawn in dash blue here. Um, you know, let's say that we really this is the number of data points we actually have in our data set, very small, and we train like a very powerful model on this data. What can happen is basically it could be like any like kind of crazy. Let's see, maybe do something like this. Go in here like this. I don't know, maybe it goes like here, here, here. Comes out here and grabs this one. Leaves this one out, right? This. Could even do something crazy like due to something weird happening in the model. Go over there like that. Okay. So this is the decision boundary that the model has learned. Perfect accuracy on the train set, but as soon as you start, drawing new points from the distribution into this picture, you'll see that it's going to have bad test time performance. So overfitting. Like a poor general to unseen data. Kind of defined like that, okay? Well, usually you can't see a picture like this, so how do you tell? Okay, one way is, let's assume that you have a data set, okay? Take a data set like this. Maybe it has 1 million data points. What you're going to want to do is take like 10K, 10K, split it up like this. This be your train, your dev, your test set, okay? The size is here, out of scope. This is kind of assuming you have truly random data, IID, shuffled, everything like that, then you can just randomly create these partitions in the data. If you have time involved, that adds some complexity. Typically, random shuffling a data set where time is an important factor is a big no-no. You probably want to have you probably want to sort this by timestamp and then take the later data as your test set and your dev set, but let's not get into that. Okay, so we split this data set up. There's a dev and test here. Test is something, theoretically you want to just kind of throw into a safe and lock it up until the very end of the project. Dev is a holdout set that you can use to aid in the development of the model. but it is possible to overfit to a dev set. Um, Obviously not directly by training on the train set, since the training algorithm does not see the dev set. But as soon as you start iterating, um, using the dev set as some kind of signal to you as a human, or even if you're doing like hyperparameter tuning, um, if you start iterating using the dev set as a signal out to some outer loop, a loop outside of the training loop, whether that be in your brain as a human or a hyperparameter tuning algorithm like Optuna or something else, you definitely can overfit to your dev set, believe it or not. That's what the test set is for. At the end of, you think you're finished with the project, and like before we go into prod, you can take the test set out of the safe and see what your real world performance will be, and also see if you did overfit to the dev set. Yeah, in a lot of use cases, that's kind of where the skill set and seniority of an MLE comes in, is to basically prevent or manage the overfitting risk to the dev set. Anyways, so the way you could tell, for one way, is take your training data, like X train, Y train, pass it through your model, and compute metrics, performance metrics for your train set. Okay, then you go ahead and do the same thing with your dev set, pass it to the same trained model, okay, and compute the same metrics on the output of the model given the dev set as input. Okay, so like let's say maybe we'll just think about accuracy as the metric, kind of naively. If we have like a 95% accuracy on train, then like a 10% on dev, this is overfitting. This is how you tell. You can see cases where like maybe you do have 95 on train and 85 on dev. This is not horribly overfit, and it may be okay. It may be possible that this, as long as your dev metrics are good, even if you have some overfitting, if you trust your dev metrics to be representative of the real world, then maybe this is okay. And you may run into cases where some overfitting might be required to like really minimize the dev metrics. And again, that's kind of where seniority and skill and the art comes into play, is how you manage things like that. Okay. But then, this is assuming, you've already finished the training run, and in some cases that can be really quick and easy and cheap. Some models can train in less than 5 seconds, depending on your data set size, how many parameters in your model, blah, blah, blah. But for training big neural nets, especially like LLMs, large ones at least, you gotta do a little bit more than this. Okay, so what you typically see here is you will see a loss curve. Loss curve. Okay, so this would be your loss on the y-axis, time, batches processed, epochs processed on the x-axis. Okay, and then you will see at the beginning of training, your train loss will be high, and it will steeply decrease, and asymptotically it will approach 0. Okay, And ideally what you would see is also on the validation loss, you should see them tracking, until at some point you'll start to see a divergence, and then at some point the valid loss will, what the hell? Start to climb, okay? Um, you know, you probably want to stop training somewhere in this range here. So either here in this little range here, you can use an early stopping technique where you're kind of like basically building this curve in real time as you process through batches, and you keep track of what's going on with the curve, and you can notice if this gap starts to grow and become significant, or importantly, if there's a point here where the the validation loss actually starts going up. That's also another sign of that you should be done. You can also use checkpointing. Because really what you want is like, you kind of want like this model, right? Do not want this model. This model is overfit. It's garbage. You want a model as it exists somewhere in this time frame. So either you should stop training at this point, or also you typically will be checkpointing. So like at each like batch or whatever, you'll like just export the weights to disk or to S3 or something like that, and you can always go back and grab an older version of the model. Okay, so that's that. So how do you deal with overfitting? Um, More data, big time. If you can get more data, get it. A lot of times you can't, but maybe then you can use some kind of like, why is this such a pain? Use like some, oh my god, synthetic data, augmented data, something like that. Thinking about this point cloud over here. If you were to like sample from this distribution, a million times, this decision boundary will become more clear, and these little bits of noise will be less impactful and less picked up on by the model training. So that this is big. If you can get more data, that's probably the best thing you can do. Other than that, it's basically weakening or constraining the model. Or okay, and like early stopping, I would argue that is kind of like weakening or restraining the model. You're stopping it early, it could keep going, it could become more powerful. You could actually, reduce the number of parameters. Or layers. You could like set max depth if you're using a tree based model. could choose an entirely different model. And there's plenty of other things you can do in this space, but what I want to get to is a regularization. Okay, that's kind of the key here that we're going to talk about, key point. So let's talk about regularization. Okay. You have typically you have a I'm just going to give some more space here. You have a loss function, which is going to be equal to some average of the loss on individual data points, right? Then typically, okay, and then in a neural network, all right, which is what we're going to focus on. You have your model. The transformer, which I'm not going to actually draw out fully here, but it's like a bunch of stacked layers of attention and feed-forward networks and things like that, right? So like there's a lot of individual weight matrices in here. So like the actual parameters of the model can be defined as a set of weight matrices. Okay, where these are all matrices. Okay. So let's say we just want to focus on training, like just one of them. We'll call it W. Okay. So we want to know what is the derivative of the loss with respect to that particular weight matrix, right? Depending on what this loss function is, like it could be cross entropy. It could be like mean squared error, etc., etc. Some function of the prediction and the label. Okay, not concerned with that here, but through backpropagation, starting with this loss function here, you can compute some term here in the gradient that comes from backprop. Okay. Now with regularization, what we do is we add this term lambda divided by 2 times b, so we normalize it by the batch size, and why does things suck? Okay, summation over w in theta. So this is a set of weight matrices. We're going to sum over these, and take the L2 norm of the matrix, where the L2 norm is defined as sum I, sum of j, wi, j squared. Okay, so it's just a sum of the individual squares of all the elements in the square matrix or rectangular matrix, right? And then here we're summing over all of the matrices. So this is really simply this part. It's just like iterating through all of the individual weights and all the matrices, squaring them and summing them together. Okay. And So again, we're looking at the derivative with respect to an individual matrix, right? We have some term derived via backprop that is originating from this loss function term, but now we have a new term in our cost function, what we're trying to optimize, and the gradient here for this matrix will be, make sure I get this right, basically take the gradient of this term, which will be lambda over b w. W here, same w, okay? And then let's remember the weight update, right? So w is going to be set to w minus the learning rate times the gradient. So what's the change in the cost function with respect to this matrix, okay? Which is going to equal w minus lambda bp minus lambda, or sorry, this is alpha over b w, okay? So this term is literally subtracting some fraction of w from itself, okay? So it's like a weight decay. Okay. This is a good regularization technique. Why is it good? I feel like the intuition's kind of tough here. You know, basically we're penalizing large values in the weight matrix, right? Large like absolute values, right? Like positive or negative, and we're actually penalizing large squares of those values, right? This is the L2. This is L2 regularization. I should probably L2. Okay. So it's really pushing down these values in the weight matrix. You know, the bigger they try to become, the more harsh the penalty. You know, because we're squaring it. So it's really pushing it down to try to be close to zero. And actually in the logistic regression case of L2 regularization, it's equivalent to assuming a Gaussian prior over the weights. Okay, so it's really pushing the weights in here towards zero, and further you get away from zero, the less probabilistic it is under the prior, and also the harsher the penalty of this term becomes. So it's really keeping all of the actual values, individual elements in the weight matrices, like kind of in this Gaussian, you know, the high density region around zero. So, and I think the intuition there is, you know, large values of W, large values of individual elements in these matrices, like maybe an element became, you know, 100 or something. And then another layer or another matrix, there's like a negative 100. And there's kind of these like landmines of high magnitude numbers scattered throughout your network. I think the intuition is there that this is going to lead to like kind of explosive and spiky and sensitive behavior in the flow of computation and data through the network. Okay, so by kind of ushering all of these values down to be a small number and then all sharing about the same range, that just results in a more stable, smoother flow of data through these tensors and these matrices. Okay. Um, and it also kind of it does it like constrains the model, right? Like it's really limiting the capacity of the model. It's not the model does not have the ability to just go anywhere it wants with these weights, right? It's being like really forced to like operate in like a certain range of values, which is like operating in this little Gaussian is a lot more constrained, a big constraint compared to if it could um, operate anywhere on the number line. So we've kind of like taken away some capacity from the model in that way, which follows the weakening or constraining of the model. So, anyways, in practice, this works well, it seems, and yeah, most popular type of regularization. Okay. Now, last thing to talk about here is dropout. The heck? Okay. Um, so let's look at a little neural net real quick. Okay. Okay, so we feed data in and we get prediction out. Dropout defines this probability. We'll call it P dropout, in the range of 0 to 1. Really probably set to something like 0.2 to 0.5 in practice. And during the forward pass of the network, we just kind of flip this bias coin for every individual neuron, and if it lands on heads, we take it out for that forward pass, zero it out basically, and do this for every forward pass. So you can kind of imagine, like if these neurons are either lit up and on or dark and off, during training, this thing is like just like a Christmas tree of lights just flashing on and off randomly. And why does this work? Well, I guess from a super high level, it is definitely constraining the network. It's taking away, like literally taking away capacity. It's like effectively deleting random parts of it, taking away, you know, capacity. And not only is it doing that once, but it's changing at every iteration. So it's really throwing like a major curveball at the model to learn still, while it's there's a high degree of uncertainty as to like what resources are even available to it at a given time. So kind of like spread out knowledge about the data and spread that out to all over the network instead of having these highly concentrated neurons that you don't want to have just one neuron in the network that is responsible for detecting faces or something. It's like that there are more kids in the classroom that can solve that problem. And the one I like, I guess, is it's the ensemble intuition. So it's kind of like training an ensemble of many smaller subnets. Okay. Um, every time you randomly turn off, 20 to 50% of these, that's got like a new network, um, and you're doing this a whole lot. So you're basically training thousands of unique models here simultaneously. So that's how I kind of like to think about it. But pays. Um, so, and then the scaling. There's a scaling issue, right? Like train versus test, uh, activation, scaling. Okay. When you're turning off, a bunch of random neurons that are just like outputting zeros to their downstream models or neurons, you can imagine that on average, like at every layer, the magnitude of the activations is going to be lower than if you were not turning these off. Okay, and we do not run dropout at test time, so there is an imbalance here between train and test time in the magnitude of the activations, which would be bad, um, would operate properly. So the fix to that is something called inverted dropout. You can manage this on at test time or train time. I think inverted dropout does something like during training, it just applies like a 1 over p scaling factor to the activations during um, wow, Python notation. That way, you don't have to worry about it at test time. So yeah. Anyways, this is overfitting, train, dev, and test sets. Um, Identifying overfitting when it happens. Um, loss curves, early stopping. Talking about the quantity of data and its role in overfitting. Um, and then talked a lot about combating overfitting by constraining the model. You can use a smaller model, take the neural network and take some layers out of it, make the layers more narrow. Um, if you're using trees, you can do things like don't let the trees grow to full depth. You can set the max depth to 3 or 4. And in fact, I think it's pretty often to set the depth to just 2, like tree stumps. They call them stumps for like XGBoost and things like that. You could try a different model entirely. I mean, maybe this is a simple problem. You don't need XGBoost or a big neural net. Maybe you can just use like naive Bayes or logistic regression or something, or linear regression. But regularization is a common and very important piece to combating overfitting in practice. So we talked about L2 regularization in the context of neural nets, drew the connection to kind of like the map solution to uh, classification, like assuming a Gaussian prior on the weights, which is a nice intuition, I think, and showed what adding this, we add this additional term to the loss, and kind of show what that looks like for a individual weight matrix, what is the difference in the update going to be? And we showed that it's actually just going to be the shrinking W linearly by some fraction of W. And then we talked about dropout. So yeah, that is it.